Here's some additional practice with these voltaic cells. What combination of anode and cathode would make the most voltage? And then write a balanced net ionic reaction. The one that makes the most voltage would be the two that are the furthest away from each other. And so that means that on this chart, I would want to do the highest number and the lowest number. And so that would be found in these first two rows here. Now, because I get to pick, my voltage is going to be positive and it will be thermodynamically favorable. I do need to figure out which is the smallest one. That is going to be the one I reverse. That would be my oxidation half step. And then I'm going to leave the one that's larger alone. So the one on top, this is my cathode. It's also the reduction step. And that means the second one, this is going to be my anode. And this is going to be my oxidation step. So notice that the vowels go together and then the constants go together. So that's one way to memorize this. So I am going to reverse this oxidation half step. So I will have aluminum going to the ion. And then it's also going to change the sign of my voltage. So because it's negative, it's going to go positive. I am going to use the silver aluminum combination. And then as far as writing the balanced net ionic equations, when I look at both of them, I see that aluminum has 3 electrons, but silver only has 1. So I need to multiply the silver by a 3. Now you don't multiply the voltage by 3. You keep it the same. So I'm going to add these two equations. So here's them all written out. I'm going to cancel the electrons. So I have 3 that are being lost and 3 that are being gained. And I'm going to bring everything down. And then my voltage, when I add those two up, I get 2.46 volts. So now for these two half cells as written, we're going to find the voltage and we're going to determine if it's thermodynamically favorable. So I want to first make sure that I can balance it. And it looks like I have 2 electrons on each side, so I'm just going to cancel that out. And then bring everything down. And then for my voltage, I just add it up, just like I added these equations. And my voltage is a 0.115. And is it thermodynamically favorable? Yes, it is. And that's because this is a positive voltage. So as written, calculate the voltage and the favorability of each of these reactions. So in this case, I don't get to choose what the oxidation half step is. So I don't get to choose that the lowest one runs backwards from how the chart lists it. And so I perhaps could have a reaction that is not favored if they reverse the wrong one. Looking at your standard reduction potential chart, and it should be at the front or the back of your packet, look up each one of these and match it to the chart, figure out which one they switched. The one that they switched, make sure you switch the sign of the voltage and then add those voltages up. So let's go ahead and do the first one. So I'm going to find the equation. So both these equations I get from that standard reduction potential sheet, and then I'm just going to match them up. So it looks like I have a silver solid going to the silver ion. So that means that they reversed this first equation that I have written. So I'm just going to rewrite it with it reversed and then switch the sign. And it looks like I do need to multiply this now bottom equation by 3. So I get 3 electrons. So when I write this equation, it's going to match the one that's up above here. And then to write the voltage, I just need to add those numbers. And I get a negative 2.46 volts, and it is not favored. So in other words, the wrong equation was reversed, and so it gives me a voltage that's not favored. So in order for this one to occur without putting electricity into it, without supplying voltage, I would have to reverse the aluminum equation, not the silver one. Let's go ahead and do another one. So here are the two equations that come from the standard reduction potential sheet. So I just need to match things up. And it looks like I have tin 2 plus on the left, and over here it's on the right. So this is going to be the one that I'm going to reverse. So I can get rid of that top equation. I just reversed it. And let's just make sure that we have the correct number of electrons. It looks like I need to multiply that now first equation by 2. And then when I add them up, I get that original equation. And then looking at the voltage, I get a positive 0.617 And because it is positive, it is favored. On this third one, it looks like the first equation is as is, and that the second equation I need to switch. So I'm going to go ahead and cross that out. So I'm going to have a positive 2.89 volts. As far as my electrons go, it looks like they will cancel because I have 2 and 2. So when I add this up, my voltage, I get a positive 2.89, and the reaction is favored. On to the third equation, on to the fourth equation. So matching up the two equations, the two half reactions that are in this equation, it looks like the second one is reversed. So let me go ahead and reverse that. And then remember, this reverses the sign. I don't need that anymore. And when we add them up, I get a negative 3.78. So with that negative sign, I know it's not favored. So in these types of problems, you don't get to choose. You just have to match it up with the chart that you get to figure out which one they reversed. And then remember to multiply through so that you have equal number of electrons that can cancel, and then never touch what those electrical potentials are. So they're all compared to a hydrogen cell, and you don't touch them with the stoichiometry. So just to review a little setup like this. So this one I do get to choose. So I have to look it up. I have to look up a lead cell and a magnesium cell. So let me write the equations. So looking at those two equations, I see that the magnesium half cell is the lower of the two numbers. So this is the one that's going to run backwards. So let me just reverse everything. So we're going to have a positive voltage, and my magnesium is going to lose electrons because it's losing electrons. Then that means that my electrons are going to go this way, and they always go through the wire. So my magnesium should get smaller and smaller and smaller as time goes by, and that means my lead will get larger in mass. So because the electrons are going from the anode to the cathode, the anode will lose mass, and so what's happening is in solution, that magnesium ion, there's more of it. There is kind of a stack up in charge because of the electron flow, so that is why when the electrons go to the cathode, this cation is going to be attracted to that negativeness, and it will travel through the salt bridge into solution, and it will make it so that the electrons can keep flowing. And because the electrons left the anode side, then I'm going to have my anion be attracted to this beaker. So the whole purpose of the salt bridge is to keep those electrons flowing so that the ions are actually moving as well as the electrons are moving. And you have to have both. That completes the circuit. Again, the electrons are going to move through the wire. The anions are going to move in the solution, so move through either the wet paper towel, or sometimes they have some sort of absorbent material that can absorb a liquid, or sometimes they have a gel. But we do get a positive voltage because we get to choose. And it looks like I accidentally pushed the button for the answer key. But we just add up those two voltages, and the shorthand notation, which I don't think is on the AP exam, but this is a way to write that shorthand notation. The anode, when you write the shorthand notation, always goes on the left, and the cathode, it goes on the right, and it goes by just what you see in the equation. So I see that my anode goes from atom to ion, and then I have in my cathode ion to atom, and so that's kind of the order that you see in that shorthand notation.